a lot for the introduction. Thanks for the organizer. I mean, it's obvious that it's an enormous honor for me to be here. So I'm going to share a memory. I'm going to be quick, so I'm not going to get emotional. I'm going to be strong enough. So, but this is something I think most of you maybe knew very well Jean-Pierre, but this is something, I mean, I would like to say. So like maybe the last memory that I have of Jean-Pierre is in August 2021, while we were exchanging emails, because previously I asked me to write a recommendation letter for something I was applying to. And then, so he wrote this letter to me, he did send it to me like before the deadline, and not only that, he was also in my dossier, what I prepared, and he was correcting my French, you know, with all the accent and whatever. You can, yes, of course. So who knows me, know that like I make a mess. And then after a few months, I discovered that while he was doing all of this, he was sick. So he just discovered that he was sick. And then I felt like super embarrassed. I felt bad, I felt stupid. And then let's say that I put priorities in a different way. So this is just to say that he was very generous, as you maybe you know, and he was someone that really worked for his community, for young people. And then, so work is because of him, thanks to him, and it really is a tribute to him. Okay. So now let's start with the regularity of envelopes. And let me say that this is the joint work with Stefano Trapani. So let me fix the context. X is going to be a compact Kähler manifold. Compact Kähler. So that is smooth. The complex dimension n, and the little omega here is the Kähler form. And now I'm also going to pick another form, theta. Now I'm going to go theta. So it's going to be a 1-1 form, so smooth form, real. So theta equal to theta bar, and then closed. So that is going to define the cohomology class in the H11 with real coefficient. But I'm not going to ask any sign of it, okay? So theta can be positive, can have zeros, or can be negative, okay? And then like I assume that theta is big. What do I mean by this? So this is going to be my definition, if you want to take it like this. So this is a definition. I say that actually, so the cohomology class of theta is big if there exists a function in the set of the theta PSH function, so of PSH of x with respect to theta, and the degenerate form a priori, such that when I look at the associated 1-1 current, so theta plus I d bar of phi, this is going to be a Kähler current, and it means that it dominates the Kähler form for some small epsilon. So this is the definition for some small positive epsilon that for simplicity we can assume to be epsilon equal to 1 up to rescaling omega. Okay? So this guy here, let me tell you, is called the Kähler current. So if you, let me know if you can see the red, otherwise I'm going to stop using. Sometimes people complain. This is the Kähler current. And then also this guy, and this is just, I can always translate such a guy, and then I'm going to use normalize with sup equal to 0, so this is going to be less or equal than 0, okay? Just for later purposes. Okay, so we are in the big context, and then what we are going to consider, well, so first of all, we are going to consider a smooth function, f a smooth function on x, so it's going to be like our barrier function, and then we are going to consider its envelope. So P of f. This guy is defined, so this is definition, is the supremum of all theta PSH function, so PSH x of theta, such that U is dominated by f. So this is why I call it barrier. So here is my barrier, and then I'm considering all the theta PSH function lying under it. Okay? So this function, it turns out that is still theta PSH. Is the envelope of theta PSH function. It's still in this set. And then the question is, so the function f, we start with the smooth. We take the envelope, so we project on the set of theta PSH function. And the question is, what is the regularity of this guy? So the barrier is smooth. What about the envelope? What is the regularity of P of f? So if I want it really to be precise, but it's going to be obvious, and then I'm going to drop. So this is the envelope with respect to theta, because I'm taking all the theta PSH function. Okay, so this theta is the same as here. Okay, I'm going to drop it in the following. So if I don't say anything, is the envelope with respect to theta. So this is the question. Fair enough. And the theorem I'm going to talk about today actually answers to this question. Theorem. So this is myself with Trapani, so let's say DN, Trapani 2023. And the theorem says that P of f is C11 bar locally in the ampus locus of theta. Okay, so let me tell you who these guys are. So first of all, the ampus locus of theta actually is, I should write the ampus locus of the cohomology class associated to theta, but I'm going to drop the parentheses just for notational simplicity. So this is a Zariski. You can see or not? You can't. It's wonderful. You know, it's there, but it's not. But red, can you see red? Maybe. Zariski. I'm not going to use colors. Zariski open subset that is dense as well. And then I'm going to, so let me call it, this is going to be big omega for the following notation. And then I'm going to call sigma the complementary. So x minus omega. So for those of you who know, this is the non-Kähler locus, the Bell locus. Non-Kähler locus. Let me also give some examples that you can fix in mind. So examples. So if theta is scalar, then the ampus locus is all of x, and the non-Kähler locus is empty, as we would like it to be. And in the case, for example, where we have a semi-positive form, so for example, something that comes up after a resolution of singularities. So let's assume that theta is 0 along the direction of an exceptional divisor. Then omega is just x minus the exceptional divisor. So the exceptional divisor is the non-Kähler locus, the Bell locus where the form degenerates. This is what you should keep in mind. And then just like to complete the statement of the theorem, what does it mean to be C11 bar loc? So locally means that it's going to be regular in the C11 bar sense in any relative open subset of the ampus locus. And C11 bar, it means that P of f is locally bounded, and its distributional Laplacian is locally bounded as well. Distributional Laplacian is locally bounded as well. Locally bounded as well, meaning that when I look at the Laplacian with respect to any Kähler form that you want, so let's say the one that we fixed at the beginning, of this P of f, so in any relative open subset of omega, we are going to have such an inequality. So there exists a positive C such that I can control the Laplacian. And maybe also let me tell something. OK, this is just, so this bound here is easy. This bound is easy, just comes from the theta pluralism harmonicity of the envelope. The difficult bound, what is very difficult is the upper bound. Okay, so this is difficult. So this is what we are going to do. Okay, very good. So my plan for today is to give the strategy of the proof of this theorem. And before doing that, I have to move the blackboard. Maybe, so this is T1. No, maybe just one remark. Is that if theta is Kähler, so is a Kähler class, or big than f, so up to adding a little bit of positivity Kähler again, then this regularity theorem was proved by Berman. Regularity is due to Berman in 2019, and actually, so Robert, in order to prove such a bound here for the Laplacian, used something called beta convergence. So the approach that I'm going to use is completely different. So this approach is based on studying the regularity of complex motion pair equations. And what I'm going to use for the big and general setting is actually something that is based on Jean-Pierre's work on the regularization of closed positive currents. Okay, so two different approaches, and this one, for the moment being, doesn't work in the big setting. So we don't know how we see to estimate for the complex motion pair equation in big case. Okay, so no, this is not what I want to use. I want to use this. Because, yes, I had also another remark. Here it is. Easy, again, but I mean, like theorems are a composition of easy lemmas, right? Let's try. What I want to observe is that if I do P of f minus f, yes. So this is going to be actually just, so this is theta. This is going to be actually just the set, the supremum. Let me write it down. The supremum of, right, such that u minus f is less or equal than 0. No, is u plus f. This is what. Yes, no, but then I still, I'm going to write it like this. This is going to be, yes, this is what I'm going to do. This is the supremum of all v now. P, what I want to do. Okay, perfect. With respect to another form, as Sebastian was saying, theta plus I dd bar of f. And now the v is going to be bounded by 0. So this is just a little. You can try. So what I want to say is that this is going to be, I don't know, another theta tilde, but it's still big. This is going to be the tilde of 0. So the remark I want to make is that up to change the form, I can always assume 0. I just translated the problem. What I want to prove and what follow that this guy, the envelope with 0, with the barrier equal to 0, is actually C11 bar locally. Okay, now let me write it down what I just said. Goal of today, as I say, goal of today is to bound the envelope of 0 is okay. So I'm going to give you the strategy, at least an idea how this is going to go. Story goes back to De Mailly's work. And then in order to do that, so first we are going to consider, so given, let me say De Mailly, given now any theta PSH function, one can consider a smooth function to it, then I'm going to call it psi of phi. So like a regularization, let's say, regularization of such a function. This function is going to be defined. We are going to add an extra dimension. This is going to be very useful for later on of W view. So Z, you have to think. So this is like Z1 of Zn. So now maybe I should have said that we fix x0 in U, relatively compact in omega, and we take holomorphic normal coordinates. So now it's very precise, normal coordinates. Then I'm going to call Z1, Zn. So now you know what these coordinates are and where I'm working. And this, okay? And how this is defined? Well, this is going to be the integral over the tangent space at x, at the point z, here. And then what I'm going to do? Well, I'm going to evaluate it at the point given by the holomorphic part of the exponential map when I apply it to the vector WV times the tangent vector. And then I take a nice scatter function, so I can take derivatives of it, of the absolute of the norm of this vector. So the norm is over the one induced by the Kähler form we start with. And then I need the volume form, and I take again the volume form associated to omega, okay? So let me just, again, saying that this guy, what does it do? It takes a tangent vector, an element in here, right? In X. So this is the holomorphic part. Let me just write it down. Holomorphic. And the Taylor expansion of the exponential map. Okay, so I say that I call this guy like the regularization of phi. So why say that? Well, because actually, so some properties of fact, psi is smooth. So we can take derivatives. This is the whole point. We can really take then the second derivatives. Then psi of phi at the point Z0 is equal to phi. You can try, this is just this is 0, so this is just the exponential at the point Z of 0, this is just Z. Okay, so this is wonderful, and then we have the cutoff function or integral equal to 1. So this is wonderful. Then what else? Actually, psi, it actually depends only on the absolute values of these complex numbers, not on the complex number, only on the length. And then maybe other two facts of this function. So one can prove that there exists a constant, positive constant, such that if I look at psi, let's say Z WV plus K WV square, this is increasing in WV. And last bit, and then I'm done, at least talking about this function, is that the following quantity, we can define the following quantity, I'm going to call it lambda. So remember this guy because it's going to appear a lot in the following. So I'm going to have, this is going to be the logarithmic derivative. So the derivative over S of psi of z exponential of s or minus s plus k the exponential of minus 2s. Let me say plus. Then this guy is going to go to, when s is going to minus infinity, this is going to converge to the long number of phi at the point z. Okay? So this is the long number. If you don't know what it is, it doesn't matter. What you should keep in mind, though, is that this guy is going to take care of the singularities of phi. So I start with something singular. I wanna work, because I want to do derivatives, I want to work with something smooth. And this is our psi. So our psi actually is going to converge in a nice way to the potential we start with. And actually, in which sense? Well, yeah, here it says that actually increasing when W goes to 0. But still, I have some quantity keeping track of the singularity of the guy. Okay. Whatever, list of function. Yes, yes. Aside of what? Ah, no, yes, all right. Yeah, sorry. Sorry. So, for example, we can always consider this. Huh? Yeah, thanks. Yeah, of course. This is contradicts with that. And then for us today, I mean, this is very general. And this is the starting point on the Mailly's argument for the regularization of any current. But for us today, phi is going to be the envelope, okay? So same holds for the envelope, because the envelope is a θ/psh function. And just for notation, instead of writing p psi or p of 0, this is just going to be capital psi, okay? So the capital psi is the regularization of the envelope. And that's it. Okay. These are all the thing. Okay, very well. So now what we say is that, so definition, that psi satisfies condition E beta for beta a priori is a real number in between 0 and 1, okay? In the local chart where we are working, in the local chart where we have the holomorphic coordinates, if and only if, because it's the definition. When I look at its action, I do have a precise control. So if and only if for any, so I'm going to be in the same range where I do have smoothness, because I want to do derivatives. So I have a theta plus I d bar of capital psi. But now I'm doing the derivative with respect to the n plus 1 coordinates. So these are z1, zn, and this is the complex one. So I have a lot of terms in here. So this is greater or equal than minus a lambda, where lambda is the same guy there, zwv, plus kwv to the power 1 plus beta times d zeta square, and then I have minus k w to the power beta plus w beta minus 1 divided by 2 d w to the square for some a and k positive constant. So, okay, this is just a condition for now. But let me, maybe I have to tell you that just to be rigorous as far as I can, this is just it's like an action just to write I over 2 for the sum from j from 1 to n, small n, the dimension of dz j wedge dz bar j. And the same you can imagine is for dw. This is just I over 2 dw wedge dw bar, okay? Because this guy is a 1-1 form, so I do need 1-1 forms on the other side, okay? So this is the equality between forms. Say it again? do that, but yes, I could do that as well. It's the same. Okay. Very good. So now let's. So this is E beta, and maybe while T1 is going to come down here, I can observe that at the right-hand side, you see if beta is strictly less than 1, there is this term W to the power beta minus 1 that is negative, and it means that when W goes, this term is going to explode, and I have a minus term here. Okay, so there is something that is exploding for beta less or equal than 1. Okay. So now I'm going to write a couple of lemmas, so really 2 lemmas. And the first one, so just to relate how, so what I wanna tell you is that how the control for a bound of the Hessian of this guy, deep psi, is gonna give us the regularity. Okay? So lemma number 1, it says that if, yeah, don't hesitate to ask question in case. If assume E beta holds for some beta in between 0 and 1, and then what we can prove is that then there exists C2 that is just a positive constant, non-harm with that, and then positive continuous function C1, that's going to be C1 of Z and delta of Z, such that we have the following, so that when I look at the difference between psi at this point minus yes, be less or equal than C1 of Z, and this is going to be for, let me put it delta here, and this is going to be for any delta positive less than delta Z. And moreover, here we do have, so remark, we do have a control of this positive function, namely that C1 of Z, it looks like the exponential of the absolute values of capital phi. So absolute values of capital phi, exponential of capital phi, and delta of Z is going to be like the exponential of minus the absolute values. So what is important? Why do actually we need this kind of control? We do like this precise expression. I mean, when I say or less is up to constant, so it's really that. It's because phi was the Kähler, the potential of the Kähler current, okay? So the thing is that phi is going to minus infinity when I do approach near sigma. That was the bell locus. So this means that when I do approach the bell locus, this guy is going to plus infinity because I'm taking the absolute values, and this guy is going to 0. So actually, this inequality, like when I go close to the bell locus, it doesn't tell me anything. Okay? This bound. So this is the first bit, and maybe also this is the remark number 1. And then the remark number 2, I'm going to be a little bit, so this is T1. The remark number 2 is that, to keep in mind, our life is going to be easier in the case that theta is scalar. So if theta is scalar, this guy phi is actually smooth. You can take it equal to 0, okay? So nothing is exploding. So T1 and delta are just constants. So C1 of Z and delta can be chosen to be constant. are constants. So there is nothing exploding in that case. And it's going to be easier. OK. This is lemma 1. And as I promised, I have to tell you about lemma 2. Lemma 2. Lemma 2 tells us that if there exist C1 and C2 such that psi of x delta minus the envelope at the point x divided delta square is dominated by C2. No, C2, I use it here, and C1 is here. For any x in a relative compact subset of the Ampus locus, then the envelope P of 0 is locally C11 bar in omega, in a sense as I said before. Okay, if you want, is C111 bar in this U, but U can be whatever. So it's going to be locally in C11 bar in omega. Okay, so just one bit was lemma 2. Lemma 2 is very classical. So people knew that this is what we have to reach. If we are here, we are done. Okay? But then let's like to put together lemma 1 and lemma 2. Lemma 1 and lemma 2 tells me that if I can get E beta equal to 1, E1, then I'm done. Because I have the 2 here. So the goal is to prove E beta, that is going to be there, E beta for beta equal to 1. Okay, and this is what we are going to do. Does it make sense? Sure. It's like at some point, you have to believe me in some sense. Okay, so so this is what I want to show you. So it's like I'm going to go like step by step, like to tell you a little bit about the strategy for this, how to prove these Hessian estimates. But before, I have to go back. Before this, I have to go a little bit back. I'm going to be quick because time is running. I have to tell you something about the proof of lemma 1. About the proof of lemma 1. So actually, the key point, and here you have to believe me, the key point to prove such a lemma is to construct a candidate for the envelope P of 0. So a candidate, what does it mean? I want to construct a theta BSH function that is less than or equal than 0 for the envelope. And how do we do if we have E beta? Well, we consider f. I'm going to call it f. This is going to be still a function of 2 variables, of n plus 1 variables, z and w. And this is going to be my capital psi plus k prime of the absolute values of w of 1 plus beta. Okay, where k prime is going to be a constant big that is going to make the game right. Okay, so it turns out, so this is what we consider. Consider this, and then exercise for you. This is not very difficult. Is that given E beta, using I beta, we can actually we can compute the Hessian of this guy, stay with respect to the n plus 1 variables, and then it's going to be greater or equal then minus A lambda, let me just write lambda, plus K times this. And make the standard metric. So, and then I got plus W to the power 1 minus beta, and then I have something in the parentheses that I'm going to tell you. Here they are. So it's something of the type beta minus 1 over 2 divided by 2 is still on the power. Why not? K prime minus K minus 1.5. And this is with respect to W square. Okay, so just so you compute, you use E beta and you have to compute the Hessian of this. But this is easy, right? This is just one variable. I mean, we can do that. You can do that. And the point is that if we choose, now we are going to choose K prime big enough such that this quantity here is going to be positive. So because if we do that, then actually we are going to end up with something whose Hessian has a loss of positivity, but it's going to be very small. Okay? Here it is, lambda. Okay? Anyway, and this is like, I cannot tell you more, but if you are interested, I'm going to be more than happy to tell you more. Anyway, this this control of the Hessian, so when I can throw out, in a sense, the term in W without thinking about this, this is going to be the key to prove lemma 1. Okay? Anyway, you're going to see why I told you all of this. Up, this is the 1, and then down. Okay, this was lemma 1. Yes? Say it again, say it again. I know, but the point is that the candidate for the envelope, maybe I can write it here and then erase. Sorry, okay, yes, now I know what I have to do. Yeah, the candidate for the envelope, no, this I'm not going to erase. I'm gonna write it here. So I have this F, and actually, I mean, we have to work a little bit more. So we are going to do, we are going to consider the infimum, because there is still this lambda that we have to make a game with it. So this is going to be the infimum of F minus C or log of W. And this C has to be small, because we want the loss of positivity to be small. So we still, and this is the infimum over the omega in between delta and 0. So we are going to consider this. And this guy, so then we can compute the theta plus I d bar of psi of this guy. And this is going to be just with respect to Z, as you say. And the candidate for the envelope is going to be something of the type mu. Oh, OK, I'm going to write it down. If you do that, the loss of positivity is going to be something like AC plus K times delta to the power 1 plus beta times omega, if you want. dz to the power square is comparable to omega in this chart. And then the candidate for the envelope is going to be, so let me call it this C0. And mu is going to be this. I'm just going to do a convex combination of two things that I know. So mu of this plus 1 minus mu of the potential of the Kähler current. So this is going to be the candidate. Yes, sure. No, for the moment, this is just an assumption. I'm saying if E beta holds for some beta in between 0 and 1, what I can tell you is that what I can tell you is that I have this estimate there with the delta to the power 1 plus beta. Yes.
But beta minus 1 is negative.
No, but there is the square.
Oh, it's square.
Yeah. Yeah, yes. don't scare me. Anyway, maybe since I say that, so this here, this delta, this loss of positivity that we can control, this power here is the same power is going to be in the is going to appear in the denominator of the lemma. Okay, so having an estimate with delta equal to 2, with beta equal to 2, so delta to the power 2, is related to have a precise control of the loss of positivity of deviation with a delta to the power square instead of 1 plus beta, okay? So this is very technical, but sometimes it becomes a game. If you don't know, you don't have nothing else to do. Okay, so, yes? So this is Schiessemann. F of Z and W. F was that one. So F is Z and W, and then you take the infimum over, I mean, this is just depends on the absolute values again, okay? So this is the point. This is why it's Schiessemann. Thanks for the question. I'm not cheating yet. And I realized that I used the orange that you cannot see. Very good. Anyway, so now, last 20 minutes. I wanna give you the proof, the strategy of the proof, or how do we get E with beta equal to 1, E1, okay? So back to the goal. That is there, prove E1, okay? Strategy to prove E1. For proving E1. And it's going to be, the first two steps are kind of in a iteration argument. So first step is that we prove E0. We prove E0. Actually, this is already it was proved already. It was there in De Mailly's paper. So I'm talking about the paper of regularization of closed positive currents, so published in 1994. But otherwise, there is an alternative proof in the emission setting by Ecology and Nguyen. Ecology and Nguyen. And this was later on in 2019. So E0, so with beta equal to 0, is fine. And then what lemma 1 does tell me is that these positive functions and positive constant such that psi of z delta minus p of z evaluated as z of delta, just delta, is less or equal than this constant for any positive delta smaller than the I, there was something like exponential or minus absolute values of phi. Okay? Okay, so we have this. And now what we do, so this is going to be step 2. We inject this information here in the De Mailly machinery. So what do I call De Mailly machinery? Not in the paper, but here. Is that, so what Jean-Pierre does is actually he takes this psi here, and then he was courage enough to really do the derivatives and compute the derivatives. And sometimes it's like, so this 0 is like we forget, we put in the bin a lot of terms, and then we get E0, that is the easier one, is the one with the less information. But if we have more information, we get more in this machine. And what we can prove injecting again. So we use this information, this bound, and we get a bound for the action of this capital psi with beta equal to 2, but with function as coefficients. Functions as coefficients what do I mean by that? More precisely, what we can prove, I mean, and this is like a lot of work. What we have is the following estimate. No, this is too early. Yes, here it is. So this is the estimate that we have as the second step of the iteration. So the Hessian still like in n plus 1 variables is greater or equal than minus a lambda plus k, let me put a square of z times w to the power 2 times dz square, and I get minus k of z, the absolute values of w, plus 1 over 2 times the w square. Okay, and then so this is what I mean by function as coefficient, namely that you see here, if you want to compare now this guy with the guy at the right, the blackboard at the top at the right, we have 1 plus 1 in here. So it's beta equal to 1. We are very happy about it. Where was it? Ah, no, it's here. Sorry. We have beta equal to 1, so this is just 1.5. This is why I do care about writing this. But instead of having some constant, I have functions. This is a positive. It's going to be a positive continuous function. Let me go back on the white. Continuous function. And again, this is going to look like absolute values of phi exponential of capital pi. And this guy, once again, is going to explode when we approach the boundary of the Lampus locus. Okay? So why this is not enough to get our lemma 2? Why this is bad? Well, because, let me see if I can tell you, I can erase. Why this is bad? Well, because I just told you a bit about the strategy of lemma 1. And the point so why this is bad? Why is this is star, let's say, okay? Why is star not good enough, let's say, because, I mean, this is nice. Not good enough as it is to get the end. Well, because as I told you, here, the key point was to construct this envelope, and we start with this f, okay? So let's try to mimic the proof. And then if we try to mimic, we should start for something. We got f of zw of what? Of psi plus, here we got our absolute values with, of w with beta equal to 2. But k prime should be something that it depends on z, right? Because k prime was the constant that helped us to kill the term in w, okay? But then, I mean, if we mimic, we should consider that. But then, what about, we should still do the second derivative of this guy. In particular, we should take care of the second derivative and the first derivative of k prime. And we don't know nothing about it. So the point is that, the problem is that we are not able, we cannot control k prime and its derivatives. We cannot control k prime and its derivatives. K prime is now a function. But still, yes. Yes. Yeah, still, but the envelope is something global. So you want something that is theta PSH globally, not just something in the open set. So this is what all the point. So this is why I say the key point is to construct this global envelope. And here we are using the global geometry, the fact that we are in the compact board with the manifold. And we want to construct the envelope. To construct the envelope, we need a bound for the Hessian, but then the bound has to be something that we control in a global way. So the inequality theta plus IDD bar of your guy, it was you there, has to work globally. Okay, anyway, this is bad. How do we do? Well, okay. What actually, so naive idea, that then it turns out to be the right one. They say, okay, you don't like this term. I don't like. You shouldn't. We don't like this term. And then what we do, we perform a change of coordinates in order to kill these guys. But then what does it mean, this change of coordinates? What it's going to be? How it's going to look like? And so this is why, in order to make rigorous this change of coordinates, so this is going to talk about just a change of coordinates, we shift our problem on a line bundle, and we do so trivializing the line bundle is going to correspond to changing the coordinates, a change of coordinates. Okay? Yes? At the end of the day, no, because I mean, at the end of the day, doing this game with the line bundle, so like we go on the line bundle and we project again, in a sense, we do find the initial estimate with the delta square for a function. But in order to construct such a function, we do perform this game. So this is just a way to make it rigorously, in a sense. And also to understand who is going to be this change of coordinates. Okay, so let's talk about that in the last 10 minutes. Let me decide who I'm going to go. So I'm going to go there. No, I wanna replace, the idea would be W to the power 2. This is what we like. We do like this. No, more or less. But I'm going to tell you explicitly what it's going to be. I mean, unfortunately, it was not so easy, so I suffered a lot. But I didn't give up. Eh? Yeah. Maybe someone is going to find a better way to do it without suffering. Okay. Yeah, still now I can erase it. Okay. Let's do it. Last bit. Well, maybe there is a good point to make a remark that is somehow related to both MI and draw questions, like remark. As we noticed already, if the class of theta is scalar, we notice that d of z, c1 of z, and hence k of z can be chosen to be just constants, positive constants. Because phi is 0, there is nothing exploding. So actually, my bound for the Hessian is just the bound that I wanted. So star is good in this sense. Star is exactly equal to a 1. Then we are done. Okay? So this reproves the regularity in the Kähler setting using this other strategy. Okay? So the Kähler setting should be easier, in the sense it is. Step 1, step 2, okay, we are done. Okay? Okay. This was the remark. And now let's go. So as we say, the goal now is to kill k of z, in a sense. And how do we do? I say that we shift to a lambda bundle, change of coordinates. After shifting the problem to a line bundle. I'm going to tell you line bundle. So how do we do? So first of all, after a modification, so like a sequence of blow-ups with smooth center, we can assume, without loss of generality, let's say, okay? So now you can believe me. I'm out of time. We can assume that this guy, this capital phi, taking care of the bad behavior at the boundary of the Ampus locus, can be written as globally as the sum of some constant that I'm going to call it Aj times the log. So let me write it, the formula of sigma j with respect to Aj to the power 2 plus a smooth function, where Hj here is a smooth Hermitian matrix, smooth Hermitian metric on a line bundle, then I'm going to call it Lj, that is the line bundle associated to a divisor, and this divisor is the one defined by the zero locus of sigma j. So sigma j is the section defining the divisor, and this is just because up to a modification I can write my Kähler current as Kähler plus sum of a divisor. This is something that Simone used yesterday as well. Okay, so I have line bundles now. Who is gonna be my line bundle? So first of all, we consider L as, so first of all, I take all the, let's say here I go from 1 to capital N. I have a capital N divisor. So I take all the divisor, I tensor. I have again a new line bundle. And then I'm going to take it to a large power. So M is going to be large enough. I'm going to choose it in a bit. And then the line bundle where I'm going to shift the problem on its dual. Okay? And maybe in order to do that, let me also say that here I'm going to call it S. S is going to be just, I take all the sections, I'm going to tensor, and then I'm going to take it the M power. I mean, it's like I would take capital N equal to 1. It's going to be the same. Okay, so now how I'm going to switch the problem? Well, I'm going to define, first of all, W. W is going to be it's going to be in this dual. So it's going to be all the beta in the dual man of the zero section that I don't like. It's very analogous to the fact that we don't like W equal to 0. It's the same. Here we don't like the zero section. Such that, so what I do is the following. I look at, so sorry, maybe I should tell you that the projection, P is the projection over X. So I take P of beta. So it's going to be an element in here. Actually, P of beta is going to be in the Ampus locus. Okay. Then I take the section of P of beta. So I'm back to L. And now I apply beta. So now I'm on L star. But actually, I'm on the fiber of a star. So this is a complex number. And I take its value, and then I'm asking to these values to be small enough. So it's going to be something like, again, this was our delta before. So, okay, this is very, what is that? Actually, W, it's the same. So this is going to be in C. You should think of W as X cross this, the complex number in between delta and exponential of minus capital phi. This is actually just the same, but like our problem is shifted, really the same. And then what I do define the function psi tilde. Psi tilde is in here, so now I'm just I'm shifting the problem. So what is this? I take beta, and then psi tilde of beta is defined as psi evaluated at the point P of beta. This is our Z. And the W is this. Okay? Anyway, this is a lot of fuss for almost nothing. A lot of parentheses. Take all the parentheses you need. But anyway, now what we want to do is, what we would like to do is we take, let's say, we choose now, we trivialize a star such that psi tilde of beta is actually equal to psi of z giz c, let's say. My change of coordinates is going to be here. So this was W at the beginning. So now something different. And this gi here of z, it just is equal to, so this is how I trivialize things, and this is going to be my change of coordinates. This is going to be, so let's see that in a local chart, the I call sigma j, this is just the holomorphic function, because I want to work with function. And this is just going to be, so this is I1 times In, so it's like all the section of the divisor to the power m, because I'm working on L star, right? So I have the power m. And then, yes. So now what we are going to do, what we have to do, we have to look at the DD bar of psi with respect to z and c. So this is what we should do, right? We're going to use this change of coordinates, and we are going to have a lot of bad terms. Bad terms, so let's say. Bad terms. And these bad terms include, I'm going to be very quick, sorry, I'm out of time, include something like k of z times gi of z. But actually, the point is that what we prove is that with this choice of the change of coordinates, this guy here is going to go to 0 when z approach the bad locus. Okay? And this is going to make our life better, and this is what is going to allow us to complete the proof. Okay, I'm going to finish here, and I'm going to take more of your time. Thanks a lot for your attention.